Okay, so we're still in chapter 6, section 6.1. We talked a little about it a little bit last Thursday? I don't remember if we started or not, but I know we talked about it on Monday, and we're going to talk about it again today. So we're talking about what happens when we have a triangle that isn't a right triangle. What can we use to help solve triangles that aren't a right triangle? So we've talked a lot about the law of sines. We talked about it when we have an angle, side, angle. So when we have angle, side, angle. So when we're given two of the angles and one of the sides, angle, angle, side. I knew that didn't sound right. Angle, angle, side. That's really easy, right? Because we have two angles. We can easily figure out the third angle using 180 degrees and then figure out the sides from there. And then we spent a lot of time on Monday talking about, well, what happens if they give us two sides and an angle? And that's where we can end up with, different solutions. So we can end up with one solution to the triangle. We can end up with no solutions to the triangle, and we could end up with two different solutions to the triangle. So we talked about that. The thing that is not on your notes, well, actually it is on your notes, it's handwritten on your notes. It's kind of written at the bottom and where we kind of left off. And that is that there is actually a nice formula. And actually, I'm going to look in your book here to see if it has a name. I feel like it has a different name. There's actually a nice formula that we can use to find the area of an oblique triangle. That just basically means a non-right triangle. And it actually uses the sine as well. So it should be written on your paper. But let me pull this over and I'll go ahead and write it on the screen when we do it. So this is one of those, it's a nice, easy formula. It helps us to figure out the area of a triangle and without having to solve everything necessarily. No, we do have to solve everything, but no, we don't have to solve everything. That's right. Okay. So let me write it here on the screen. So the area of a triangle, and it does not have to be a right triangle, can be found by doing 1/2 side B times side C times the sine of side A. Okay, or it could be 1/2 times A times C times the sine of B. Or it could be 1/2 times AB times the sine of C. Okay, so what you'll notice about this is it's really similar to the area of a right triangle, right? Except we have this whole value of the sine of C. So this holds true, just to kind of give you a quick little proof. This holds true if we do actually have a right triangle, right? So if we popped up a right triangle here. Okay, so do you remember what the area of a right triangle is? Well, actually any triangle, but the area of a right triangle. It's probably hard to type in the chat, right? Area, if I can get my pen working. Yep. Area equals 1/2 base times altitude, or I'm going to use h for height, base times height, right? So this is our base, and this is our height. So if I would apply the area formula for oblique triangles, what I would have is this is an angle opposite my height would be h. And so the third remaining angle that we would use to multiply by the sine would be the sine of 90 degrees, right? And if you remember, or you have your unit circled, the sine of 90 degrees is just 1. So it works in right triangles, right? Because we're using that 90-degree angle as our angle that we take the sine of. But this case actually lets you use it for any triangle, which is nice to have a broader case. So these area formulas for oblique triangles, they're basically just a plug-in kind of a thing, a memorize and plug-in. So let's try one out. Erase what I got here. Okay, so let's see. We'll pick number 22. So 22, we have an angle A that's 5 degrees and 15 minutes. We have side B is 4.5 and side C is 22. So if I want to find the area of this triangle, I can do that because they've given me two sides, right? They've given me side B and side C, and they've given me the angle that does not oppose either of those sides. Now, all of these examples, they kind of made it nice, right? It made it nice and easy. So if for some reason they had given you angle B, then we would have to go back and use our law of sines to solve the whole triangle and then find the area. But in all three of these problems, you can see that they've made it nice and they've given you two sides and the non-corresponding angle to it. So that's nice and easy, right? All right, so then we just pick the appropriate formula. In this case, it's going to be the first one here at the top, right? 1/2 sine, 1/2 B times C times the sine of A. So for 22, we're going to do the area equals 1/2 B, which is 4.5, times C, which is 22, times the sine of 5 degrees 15 minutes. So if you remember how to turn minutes into decimal, we're just going to make this. So it's 15 out of 60, 1 out of 4, or 0.25. So once you've established your equation, then it's just as easy as putting it into a tool to help you figure out what it would be. So how about Desmos? I think I have Desmos. Yep, I do have Desmos up. And we would say that the area is I'm going to change to decimal before I forget. Or to decimal, to degrees before I forget. Okay, 0.5 times 4.5 times 22 times the sine of 5.25. And we get that the area is 4.53. And we don't have any units on it, so we just say that the area is 4.53. Easy as that. So this one's just a matter of knowing the formula and plugging it in. There's not a whole lot of trickiness with it, especially when they're giving you triangle sides and angles that are opposite each other. I don't think they even give them. I have my book right here. I'm going to double check. Yes, all of them, 19 through 24, we have the angle is not correspond to either of the sides that they give to us. All right, so that's the angle formula that we have. There's one more problem on here, which is a real world problem. So if you notice on your homework, well, you guys are probably all still working on chapter 5, but once you get to chapter 6, number 25 and number 27 are actually more real life problems, if you want to call them that. And so we have example number 26. I think it's just helpful to kind of go through one of these. So let me pop that up here. I know. Okay. So for these problems, I highly, highly recommend drawing a picture. Actually, number 27, when you get to your homework, has a picture. Number 25 does not. So I think it's good to always, I don't know, in math, I think if you can draw a visual of it, it always helps, especially with any kind of triangles. Even if your triangle is completely off, which I know I've drawn a lot of off triangles before with angles that aren't correct, still kind of gives us a sense of what we're talking about. Okay, for this problem, it says you are standing 40 meters from the base of a tree that is leaning 8 degrees from the vertical away from you. The angle of elevation from your feet to the top of the tree is 20 degrees 50 minutes. Draw a triangle that represents the problem. Show the known quantities on the triangle and use a variable to indicate the height of the tree. So I actually did this problem a little bit different than they did the problem. So Jennifer, I'm going to ask your opinion too, what you think of the of this problem. So I did it both ways, but let's start by making a drawing. So if you have your paper in front of you, you can make a drawing too. My triangle, so we know, let's see. This is going to be awesome when I'm drawing on paint here. Okay, here's me, right? And then I've got the ground and I'm 40 meters from the base of a tree. Oh, that's bad. The ground is very uneven here. Okay. Okay, so the distance from me to the tree is 40 meters. Okay, now it says the tree is leaning 8 degrees from the vertical away from you. So a normal, not a normal tree, but most trees don't grow straight up, but a straight vertical tree would be at 90 degrees, right? But it's 8 degrees away from us. So our tree actually is going to be like slightly like this. That's an exaggerated angle there, right? But we'll just make this like our vertical here. Right, so our tree is going to be like this. And the angle that it forms with the ground, if I can get my thing right, this angle here is going to be 90 degrees, which is vertical, right? Plus the additional 8 degrees that it's going away from us. So this is 98 degrees. And this is the top of the tree. It's a happy little tree up there, right? And then it says that the angle of elevation from your feet to the top of the tree is 20 degrees 50 minutes. So I'm glad that it indicated it was from my feet, because if it was from my head, then we wouldn't have a triangle, right? So if I go up from my feet to the top of the tree, then this angle is 20 degrees 50 minutes. So 20 degrees and then 50 over 60, unfortunately, is a repeating decimal. It's not a rational number. So we're just going to make it 20.83 repeating degrees. Very lovely degree measurement. All right, so Jennifer, you okay so far? Do you agree? All right. This is where I did the problem differently than they did. They actually did a more simplistic version of it. So it says, draw a triangle that represents the problem. I was good there. It says, show the known quantities on the triangle and use a variable to indicate the height of the tree. So this is where I kind of deviated, and I'll tell you what the book said and what I thought. So would you consider, Jennifer, the height of the tree to be T, which is the actual from the base of the tree to the top of the green, right? Like if you actually just took a measuring tape from the bottom to the top. Or do you think that the height of the tree is the vertical distance from the ground? Like if I made this 90 degrees here. You think it's T. All right, so you agree with the book, so we're gonna go with that, Jennifer. For some reason in my head, I was thinking, oh, well, they wanna know how high it is to the top of the tree, but I think they actually were asking for the physical height of the tree if you took a measuring tape, which is actually a way easier problem because I was like, oh, we need to figure all this, and I did too much there. So we will take this off and we'll go with tree since you and the book agree. Okay. So now we have a triangle, right? And it says, write an equation involving the unknown height of the tree. We'll call that T. And then find the height of the tree. Okay, so what equation or what formula do we know that we could use to find the height of the tree T? So since we're in the law of sines section, we're probably going to use law of sines, right? And right now we have 98 degrees, the angle 98 degrees. We don't know what the distance is from our feet to the top of the tree. That's okay. We have 40 meters from our feet to basically where the tree base is, and we don't know the angle at the top, but we could find that. And we have the height of the tree T and the angle of elevation from our feet. So those are opposite of each other. So I think the one thing we need to do before using the law of sines is to figure out what this last angle is here so that we can use this as one of our ratios, right? And so since we have 98 degrees plus 20.83 degrees and we subtract those added together from 180, I end up with this angle being about 61.1, we'll just say 17 degree. And that's just basically those three angles add up to 180 degrees, okay? Okay, so now we can use the law of sines to figure out what is the height of the tree. So this is part C, right? So we have that the height of the tree, T, over the sine of 20.83 degrees equals 40 meters over the sine of 61.17 degrees. Okay, so then just to solve it, we're just gonna, cross multiply. We're gonna multiply this way. And multiply this way. And we end up with basically T equals 40 times the sine of 20.83 divided by the sine of 61.17. So then if we pop into Desmos, right, we get, and we're still in degrees, double check we're still in degrees, okay. So we get 40 times, make sure I put the right one on the top. Which one was on the top? Sine of 20, okay. divided by sine of, not the sim. And we get that the height of the tree is 16.23 meters, which seems reasonable, right? So the tree is 16.23 meters. So that's how we would do that. Okay, so number 25 and 27 are going to be very similar. We have a flagpole, and we've got a flight path where we've got some sides and an angle, and we need to figure out distances based off of our trig functions. All right, any questions about that? Yep, those should be pretty easy. These are kind of the fun ones when you get to figure out all that stuff. For the last little bit, I'm just going to introduce the law of cosines. So, and then we won't finish 6.2 today. We'll finish it up on Monday when we're all kind of back together. But I did want to introduce it so that we can, I think if you hear it more than once, and for me, it's helpful. So hopefully helpful for you guys too. All right, so the law of cosines, just like the law of sines, it's just a formula that we can use for any oblique triangle. So again, these triangles do not have to be right triangles to be able to use the law of sine or cosine. And these are used for, you can see from the formulas once we get in there, they're really for side, side, side. So if you are given a triangle with all three sides and no angles. So these are used to determine side, side, side triangles and for side, angle, side triangles. These are the formulas that you want to use for that. So what they are is, you can see them written out here much more nicely than I can write them. And they look like the Pythagorean theorem, except we have a little bit extra to them that kind of takes into the account that we don't actually have a right angle in our formula. So this top row right here is for when we're trying to solve for angle A, all right? Well, I guess the alternative form over here is when I'm trying to solve for angle A. But if you have A squared equals B squared plus C squared minus 2BC cosine A. So that's just like a bunch of words, so we're going to actually put it into practice. But really the alternative form is really where you kind of get the magic of the cosine formula. So if you have the sides of a triangle and you want to determine what angle A is, we know that the cosine of angle A is equal to B squared plus C squared minus A squared over 2BC. The thing that's a little bit different about this versus the Pythagorean theorem is that we don't actually know what the hypotenuse is going in necessarily. If you have side, 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 you do know what the longest side is, but that's still not necessarily the hypotenuse because the hypotenuse is the one away from the 90-degree angle. So this kind of takes into account the fact that we don't have, or it does take into the account that we don't have a 90-degree angle. So you can see all the formulas are very similar. It's just a difference of, if you're trying to find the cosine of angle A, then you're going to add B and C together and you're going to subtract A. And then you're going to multiply by B and C, 2 times B and C at the bottom. So I don't know, when you're kind of looking at the formulas, you can kind of see a pattern, right? When you're trying to find the cosine of B, the B is what gets subtracted and it also does not get divided down here. And when you're trying to find the cosine of C, the C is what gets subtracted and it doesn't end up getting in the denominator down here. But really, other than just kind of seeing the formulas, it's again one of those kind of plug in and figure out what does our triangle look like based off of what we've plugged in. So I think we'll probably just do one example and then do some more on Monday is what I'm thinking. All right, so let me pull these over so you don't have to watch me rewrite those. Those would take a while. And then we're going to do, let's do number 4 since they have a nice triangle drawn for us already. Okay. It's blurry, but at least it's bigger. Okay, so this is number 4 from your paper. So we have a triangle, an ABC triangle. Obviously, this is not a right triangle the way that it's drawn. Side AC is 5.4 yards. Side BC is 4.2 yards, and side AB is 2.1 yards. So they want us to solve the triangle. So whenever you see solve the triangle, that basically means find all the sides and find all the angles. We have all the sides, but we don't have any of the angles. So we're going to use our law of cosines to find this. If we had our law of sines, well, we do have the law of sines, but that's not really useful because we don't have any angles. As long as we have one angle, we could go ahead and use the law of sines, but we have no angles to go off of. So we need to use a different tool to figure out what the angles are. So we're going to use the law of cosines. So I like to label them just because that way I don't have to think when I'm plugging into the formula. So angle, since this is angle A, then side A is going to be 4.2. Okay, and this is angle B, so side B is 5.4 yards. And this is angle C up here, so side C is 2.1 yards. So I just like to label them from my personal thing. Okay, so then if I go to actually figure out, doesn't matter what, let's do angle A first. Let's figure out angle A first, okay? So we're gonna actually just plug our formula in, okay? And the alternative form tends to be the one that you use. So we're gonna do the cosine of A, okay, equals B squared, 5.4 squared, plus C squared, 2.1 squared. And then you always subtract the side that you're finding. So 4.2 squared. And then we divide that by 2, and we multiply by the two sides that are not across from our angle, so B times C. So 5.4 times 2.1. Okay. So when you do that, you get some number, right? I don't have it written down. So I have the solution, but I didn't write down what the solution to that was. So if I do 5.4 squared plus 2.1 squared, and obviously you can simplify this too if you'd like to do more simplifying, but I'm fine kind of just going straight for the calculation. Divided by 2 times 5.4 times 2.1. Okay, so I get 0.70238, this nice decimal. So this is where we have to kind of go back to that section that we did right at the end. If I know the cosine of A is 0.7 and I want to figure out what the angle A is, then what I'm going to do is I'm going to take the inverse cosine of both sides of my equation. Okay, So then I end up with A equals, and what I like to do when I'm typing it into my graphing tool or Desmos is I actually like to just go ahead and, since I have the formula typed in there, I'm just going to put parentheses around the whole thing, hopefully. And I'm actually going to just take the inverse cosine of the whole value. So then I know that I'm getting as exact as I can. Okay, so if I take the inverse cosine of everything that's in here, I end up with 45.4 degrees. If you wrote down the decimal and you went ahead and did an inverse sine, that would work too. So 45.4 degrees. So now we have angle A down here is 45.4 degrees. And that actually looks reasonable with our picture, so we know we're on the right track. Now that we have that, solving the other two, you have options, right? Since this is a law of cosines section, you might want to use the law of cosines to find the other three. But now you actually could use the law of sines to find the other two, or you can use the law of sines to find B, and then just know that A plus B plus C equals 180 degrees and use that to find C. Again, since this was the law of cosine section, I found it, the law of, I use the law of cosines for all three, just to practice it, but it's not necessary because this, once you have one angle, that opens up the possibility. So the law of sines should work if we use that. The law of cosines will work for all three angles. Yes, so let's just do one more with the law of cosines. And then, actually, let's do it kind of both ways, and then we'll wrap up for the day. So let's go with the big obtuse angle here. So let's do the cosine of B. So let's look at this angle here, right? The cosine of B. So now I have to use my cosine of B law of cosines, right? So that means I have A squared plus C squared minus B squared. So I have the two sides that are not opposite my angle, 4.2 plus 2.1 squared minus 5.4 squared, all over 2 times 4.2 times 2.1. So I feel like this formula isn't too bad to remember because it kind of has the same pattern. So then really I'm going into Desmos and I'm calculating what B is. Now I got to move Desmos to this side, right? And it kind of feels like the same numbers. I'm going to leave this same format, right? So 4.2, 2.1 minus 5.4. And in the denominator, I have 4.2. Okay. And I actually left my inverse cosine up, so I kind of skipped a step in there. But I end up with B equals 113.8 degrees. 118.3 degrees. We'll round to the nearest tenth. So just to kind of prove that it would also work, if we did our law of sines, we could say that get a little room here. Okay, we could say that, I'm gonna have my picture here. Side B over the sine of B, right, equals side A over the sine of A. Okay, and so we know that side B is 5.4 yards. So 5.4 over the sine of B. And then we have side A, which is 4.2 over the sine of A, which is 45.4 degrees. Okay, so I use the law of cosines to find the first angle, and now I'm using the law of sines to find, I use the law of cosines to find angle A, the first angle. Now I'm using the law of sines to find B, the second angle. All right, so if I do my cross multiplication, I end up with the sine of B equals 5.4 times the sine of 45.4 over 4.2. So again, we're going to have to use inverse sine, right, of both sides. I'm kind of being fast here. Inverse sine of both sides to figure out what angle B is. So if we put in the inverse sine of this, let's see what we end up with. Give us a little more room here. Okay. We want the inverse sine of 5.4 times the sine of 45.4 divided by 4.2. Okay, and so then we end up with this 66.27. And you think, oh, that didn't work. But remember that we can have two possible solutions when we do the inverse sine, right? And the other solution is to subtract 180 from 66.27. So if this is our first solution, our second solution is 180 minus 66.27, which gives us our 113.8. So it actually works for that. So then if we want to find, so we have A, we have B with it, we did two different ways, right? So now we know that this is definitely 113.8. If we want to find angle C, you could use law of cosines, law of sines, or you could just use the knowledge that A plus B plus C equals 180 degrees. So C ends up being 20.8 degrees if you do that. If it's like a test or something really important you want to make sure you get right, then do it more than one way, right? Do the law of cosines to find C and see if you end up with the same answer that you have when you add the three angles up to 180 degrees. Okay, so that is the law of cosines kind of in a nutshell. There's really not a whole lot more to it than that. We will do some more examples of it just to make sure everybody has it, but that is basically what it is. So thanks for coming today, Jennifer. Hopefully everybody online is listening in, and we will see you guys on Monday.